attendees are in listen-only mode.
Hello and welcome to our webinar about the latest trends in low-power logic devices for portable industrial applications. I am Thierry de Jong, your moderator and webinar organizer for today. Before we start, let's take a moment to ensure that everyone is ready and familiar with the webinar control panel. First, you should have a control panel on the right side of your screen. You may hide this panel by clicking on the red arrow button in the upper left corner of the control panel. You may expand the panel by clicking the same button. Secondly, you have the ability to submit questions using the chat pane located near the bottom of the control panel. Make sure you select Send Questions to Staff before clicking the Send button. We will try to answer your question during the Q&A session at the end of this webinar. As a final remark, please note that this webinar is being recorded and will be made available for on-demand playback on NXP's e-learning environment. Let's get started. Today's presenter is Cliff Lloyd. Take it away, Cliff.
Hello and welcome again to the NXP Portable Industrial Webinar. I'm Cliff Lloyd. I'm having a problem advancing my slides. Okay. So today we will look at what are the trends in the portable industrial market, what are the needs for this market, also what are the needs for the design engineers that are building the products, and also the needs of the component and the manufacturing sites. We will then look at some of the low voltage families, configurable logic and combination logic that is targeted specifically to address the market needs. Okay, so first, what are the needs? So the needs and the trends in the market today, the handsets are getting smaller and smaller. They're also being used on the shop floor, which means they have to be durable and be able to withstand the harsh environment. More functionality is being added. That means that the components inside the products need to be smaller and smaller. They are being used for measurement, monitoring, scanning, input devices. We're also starting to see wearable devices emerge. The early wearable devices that we were all familiar with were hearing aids. And then we started seeing the Nike training modules that you could wear on your arm. Also now they're being used in medical devices for monitoring, like blood pressure, heart rate monitors, hearing aids, and of course the blood glucose pumps. And logic is everywhere. We're seeing logic in all of these products, especially very small packaged logic devices. So let's first define what the industrial market is. It's a broad range of applications. It is typically B2B products. It is not consumer. It deals with the real world, input, sense, controls, devices directly, often without human intervention. They are embedded in the design. They are used in the factory for testing, monitoring. They are tooling devices, they're measurement and control. Also in medical labs for testing and diagnostics. Construction tools, laser measurement tools, etc. Warehouse uses them, in asset management tracking. Also, we see them in power and energy management. The industrial market that we're not talking about is the consumer, except for some small, home medical equipment. And of course, automotive. Automotive has its own market. So what are some of the design issues for these portable industrial applications? Of course, power is an issue. Battery life is critical. They must be able to last at least a day or one working shift. Size is also an issue. Human ergonomics, they must fit in your hand or be able to be carried on your belt or be wearable. Weight, batteries are a major contributor to the weight of the devices, and any way we can reduce the size of the battery or the number of cells in the battery would further reduce the size and weight of the application. Durability. Now that we're starting to see them on the shop floor and out in the marketplace in the industrial environment, they need to be very robust. Okay, and cost, for the most part, cost is not as critical as it is in the consumer markets. Logic is everywhere. Despite the fact that we keep hearing that logic is being integrated, we still see logic everywhere. To let you know how many logic devices are shipped worldwide, 18 billion units are being shipped worldwide. Today, logic is not just gates and buffers. It is also translators and level shifters. Switches, and not the ordinary analog switches, but also the data, the video, MIPI, VGA, and USB switches. Also, load switches. In the past, the switches that were offered from the logic groups were typically in the 5 to 10 ohm range. Now they're in the sub 1 ohm range, and for load switches, they're in the millivolt, a milliohm RDS(on) range. Okay. Logic is the glue that ties the ASIC and the microprocessor together. Just taking a quick look at some of the portable applications. Here we have a barcode reader, a portable measurement equipment, and a portable medical equipment. On the barcode reader, you can see that logic is used as Smith triggers for the input trigger, level shifters, buffers, data switches, and load switches. Similarly, for the portable measurement equipment, we see much the same. Today, we see logic mostly in the single and dual gate devices, no longer the big octal devices or the parity checkers and things like that. All that has been integrated, but logic is the glue that ties the various ASICs and microprocessors together. Okay, so what are some of the needs of this portable industrial market? You know, the products that are being made today are getting smaller and more compact. And like I said, they require longer battery life. So to get the longer battery life, we see the operating voltages dropping down because that reduces the number of cells of batteries and reduces the weight of the batteries. So the operating voltages are going from 5 to 3.5 volts and below. And the packages that are being implemented inside these products are also getting smaller. In the past, they were all leaded packages. Today, they are leadless packages. And of course, the packages need to be a lot more robust to be able to withstand the harsh environment that they are being subjected to. Reliability is extremely important, and I will be talking about the extensive testing that we have done in these packages to improve the reliability of the products. Okay, moving on now to some of the needs of the design engineers. You know, they are being challenged with improving and increasing the functionality of the products that they design. And they're being required to squeeze this increased functionality into less space. They're also being pressured to do it in faster design cycles, shorter design times, faster turnaround. And in order to do this, they are looking for more flexibility and versatility in the components and the circuits that they use. They also want to be able to reuse some of the previous segments of the circuits that they have designed. So ease of use and consistency. So when you get a product and you learn how to use a product, you don't want to have to relearn how to use it because some of the pinning or some of the specifications have slightly changed on them. Okay, and now moving on to the needs of the component engineering and also manufacturing. You know, to the component engineering, space is extremely important, and the smaller you can make the package, the better. Also, cost is important. So if you can get these products cheaper, that is important. However, if these products are so small and very difficult to use, then the cost of implementing them in a design is very costly. And I will talk about some of the things that we have done to reduce the cost of implementation by eliminating the need for a step-down mask in the printing process on the PCB. Also, engineers and component engineers need a wide selection of package options because maybe they don't need the smallest package, but yet they want to be able to use the most effective package for their application. Reliability is very important. We've done extensive testing on bending the boards, drop tests, and vibration studies. Quality, of course, that's a given. You need to have quality, you know, that is very high, something in the range of 150, 200 parts per billion. Also, multi-sourcing, dual sourcing, you know, reliability of supply is very important. And we understand that, and that's why in our operations we have dual sourcing for our fabs, our test, and our assembly operations. We have multiple fabs for the same product. We have also multiple assembly sites, like, for instance, Bangkok and ASEAN. And then for our leadless packages, we assemble in Malaysia and also in Guangdong, China. Okay, so the trends and the needs, we said the products are getting smaller, more rugged, more functionality, longer battery life, more robust, and reliability. So how do we address these needs? Looking at it from a component engineer, for the most part, the component engineer is more interested in the smaller packages and in package options, robustness and reliability, ease of use, and space. So focusing for a moment on packaging options, we offer a wide selection of package options. And the thing that's important to note here is that the die that fits in a leaded package also fits in a leadless package of the same pin count. So for all of these products here on the top row, the die that fits in the DIL package on the extreme left also fits in the thin QFN package on the right. And the reason why this is possible is because over the years we primarily focus on die shrinks, reducing the cost of the die. So now the die is so small that really the cost of the product, the end product, is more a function of the cost of the package and not the silicon inside. Likewise, on the bottom row with the pico gates and the MicroPak, the die that fits in the DP package on the left fits in the GEN package on the right of the same pin count, an 8-lead package on the left, also the 8-lead package of the GEN package on the right. Also, when you go from a TSSOP to a DQFN or leadless package, there's tremendous space savings. You can see that the DQFN package is 1/4 the size of the TSSOP package. Likewise, when you go from a pico gate to a MicroPak package, the MicroPak package is also 1/4 the size of the pico gate GW package. And you can get further space savings excuse me, by going from the GF package to the GX package. You get an additional 34 or 36% space savings. Excuse me, I'm getting over a cold. Okay, so let's focus on these leadless packages on the bottom right. The thing to note here is that as the packages get smaller and smaller, the pitch on the package, that is the distance between the leads and the packages, also gets smaller. We go from a 0.5 pitch to a 0.35 pitch and then to a 0.3 pitch for the GN package. As the pitch gets smaller and smaller, it becomes more difficult to mount these on PCBs and also becomes more expensive because a step-down mask is necessary to be able to successfully mount these on PCBs. And we started hearing from our customers that this was a problem and a very costly operation, so we focused on how we could reduce the cost of mounting these packages on a PCB, and that's when we came up with our GX package. Our GX package today is the world's smallest logic package with the largest pads. It measures only 0.8 by 0.8 by 0.35 millimeters high. It is a 5-lead device. However, the pitch on this package is 0.5 millimeters, not the 0.4, the 0.35, or the 0.3 for the packages that are actually physically larger than this one. We have it available in all of our AUP and LBC 5-lead functions. The benefits of the larger pitch is that it's easier to mount on a PCB. There's less risks of shorts. There's no costly step-down mask required, and there's no restriction placed on placing it on a PCB. When you use a step-down mask, the design engineer, the component engineer, is restricted on where you can put the component on the PCB because the whole mask or stencil for printing the solder cannot be a step-down mask in its entirety. They have to select areas. The reason for this is that when you make a step-down mask, you are cutting the thickness of the mask from 100 microns down to 80 microns or so. Let me explain to you how the step-down mask works in the printing operation of putting the solder on the PCB. Here we have a PCB with 6 pads on it. Looking at it edgewise, you're looking in and you can see the 3 pads right there. So in order to put the solder on this PCB, to print it onto the pads, you need a stencil or a mask. And this mask has vias in it through which, when you draw the solder paste across it, and this is typically type 3 or type 4 solder, as the solder paste is drawing across the mask by a squeegee, then solder is deposited in the vias. When the mask is removed from the PCB, then the solder remains on the land areas on the PCB. However, in this example, we printed 3 rows of solder balls, so that when you mount a leadless package on it, as the package comes in contact with the PCB and it's reflowed, since there's excessive solder there is the possibility of shorting of the lands on the PCB. In order to get around this, what they have developed is what they call a step-down mask. And you can see on this illustration that there's a little step here. Typically, this step down is either 80 or in some cases 50 microns. What this allows you to do is that when you draw the solder paste across the stencil, less solder is deposited in the vias, and then when the solder mask is removed, less solder is left on the PCB, thus resulting in less solder on the board and the reduced risks of solder shorts. So that is one of the benefits of this new diamond package. Although it is the world's smallest package, the pad pitch between any pads on the PCB is 0.5 millimeters, and as such, a costly step-down mask is not required. Okay, moving on now to robustness and reliability. This is another major concern of the component engineers and the manufacturers of these industrial products. So in order to determine the robustness of an assembly, we looked at the forces that are required to dislodge a leadless package, a leaded package, and a wafer chip scale package from a PCB assembly. So we looked at the pull force, and this is the force required to pull a device off the board. We also looked at the forces required to slide a device off the board. So what we first did was, on this comparison analysis, we selected a number of packages. We selected 2 leadless packages from NXP, the MicroPak and the MicroPak 2. These are a 0.5 mil package and a 0.35 mil pitch package. Then also 2 leaded packages, the SOT 665 and the SOT 666 from NXP, a wafer chip scale package, and then a couple of TI package, a Toshiba package, the FE package, and the Toshiba FSB package. You will note that the pad pitch on these packages varies from 0.65 down to 0.35. In this illustration here you see the footprint. This is the amount of space that the package takes up on the PCB. Although the leaded packages take up 2.5 millimeters squares on the board, the leadless packages take up 1.5 to 1 millimeter square. Also, wafer chip scale is 1.5 millimeters square, and the Toshiba FSB package is 1 millimeter square. We then looked at what the forces were required to pull the part off the PCB, or to the shear force to slide the part off the PCB. And this force is measured in newtons. And we were surprised to see that the leadless packages required more force to dislodge them than the leadless packages, even though the leaded packages were larger physically than the leadless packages. And then we started looking into this and as to why this would be, because a lot of people had expected that the leaded packages were a more robust would make a more robust bond on the PCB rather than the leadless packages. But what was discovered was that the surface area that comes in contact with the land area on the PCB was greater for the leadless packages compared to the leaded packages. Of course, the wafer chip scale package has another set of problems apart from the fact that the balls are smaller and make less contact with the PCB. They're also only attached to the silicon by metal, and that metal is easy to peel off. But when you look at the other leadless packages, you see that although they are physically bigger, they have less resistance to being dislodged from the PCB. So this was a good indication that the leadless packages are an ideal candidate for the harsh environment of the industrial portable marketplace that is emerging. We also looked at the reliability, and in order to determine the reliability of an assembly, we looked at what it would take to dislodge a package from a PCB with repeated abuse. So we performed extensive board-level reliability tests. We did band testing, drop testing, and vibration testing. So looking at the band testing, what we did was we took a PCB, and onto a PCB we mounted a number of components. And we did a JEDEC testing, which is a 4-point cycle bend test. And this test was performed at 1 per second. The span between the posts on the board were 110 millimeters, and we depressed this board 2 millimeters. We did this repeatedly over time, and we found that after a million cycles, no MicroPak, the SOT 891, was dislodged from the PCB. Not only were there any devices dislodged, we also did some X-ray analysis, and we discovered that there were also no solder joint fatigue problems with the devices after a million cycles. We also did the similar testing for the larger QFNs, the 28-pin QFN, and for those devices we found that there was no failures after 82,000 cycles. The JEDEC spec is 200 cycles. So again, a leadless package is a very robust, ideal product for the portable industrial marketplace. Moving on then to drop testing, and we all know how often we drop our products, our cell phones and everything else. In the industrial marketplace, the floors are typically a lot harder, just directly onto the concrete. So we also performed extensive drop tests for the MicroPak 6-lead package, and also for a QFN package of 32 leads. The stress load that we put on there was 1,500 grams, 0.5 millimeter, 0.5 milliseconds, half sign. The test duration was 150 drops, and again, this time we mounted 15 components on the PCB. And the JEDEC requirement, is that the device can withstand 30 drops, and we performed 150 drops for the SOT 891. So this is the 6-lead MicroPak without any failures, and we continued to do this testing until we got to 1,000 drops, and still there was no failures for the MicroPak packages. The overall quality and reliability of these packages is 150 ppb. That's and this is, over a 1-year period, and you can see that the quality is improving over time. It's now running at about 125 ppb. And as far as reliability, all of our MicroPak's products, both the die and the package, are designed to the AEC Q100 specifications. And then our fabs, assembly, and test environments are also spec'd to the AEC Q100. For those of you that are not familiar with the AEC Q100 spec, this is the automotive spec that is used in the automotive environment. Okay, so now moving on down to ease of use and space. As I previously said, that the die that fits in the largest package also fits in the smaller package, the leadless package of the same lead count. And we also use the same pinning. So pin 1 on a TSSOP, if it is an input, is also the same input on pin 1 of the DQFN package. I just got a message here. I got it. Okay. And also, when we're talking about ease of use, we're working on eliminating the need to use a step-down mask as we introduce smaller and smaller packages. Not only will it make it easier to use, but it will also reduce the cost of implementation. Okay, now moving on to the needs of the design engineer. He is apart from trying to get as much into the package, he is also focused on battery life, lower power consumption, lower operating voltages, so that he can reduce the number of cells that are required. He likes to have the flexibility of the components that he uses, so that he can tie the different ASICs and microprocessors together. He also needs to be able to do this in the fastest turnaround time possible. And of course, the design engineer's space and cost is also very important. So I will show you how we address these needs of the design engineer also. The design engineering is faced with many challenges. He has to come up with a compact design, faster turnaround, lower voltages. He needs to have flexibility. His design needs to be robust, easy to use, space savings, and long battery lives. And this is like a jigsaw puzzle that he has to fit together. And when he gets it all together, then he's asked to make it even smaller, so that he's asked to make it smaller to fit in the smallest space possible, so that he can get it into one of these many different products, or a host of other small devices. And we can address these needs of the design engineer with our configurable and combination logic devices. So first, looking at how do we address the need for longer battery life. There are two major contributors to battery life, or reduced battery life. It is the dynamic power consumption of the device. This is the power that the device uses when it's actually operating, doing something. And then there is a static power consumption of the device. So when the device is just sitting around in standby mode, how much power is it consuming just by being on? So we looked at a typical power consumption at 25 degrees C at 1.25 volts VCC. And we looked at three families, the LVC, the AUP family, and the AXP family. So first, looking at the dynamic power consumption. And typically we represent this in capacitance, picofarads, because this is the signal that is swinging up and down that's consuming power. For the AXP family, it has a typical 3.5 picofarads. AUP is 4 picofarads, and the LVC is 16 picofarads. So if you were to use a device in an application, and let's hypothetically say you would design your whole product with LVC type technology, it would use 4.5 times as much power while working than an AXP device. However, what's significantly more important is how much power does it use when it's not working but just sitting in standby or idle mode. And we see that the static power consumption for an AXP is 0.3 microamps, AUP is 0.9, and the LVC is 10 microamps. So you can see that an LVC device in the static mode is consuming 33 times more power than the AXP device in the same mode. So these are very important considerations to take into account when you are designing your circuits and what logic components you're going to use to provide the glue between the various ASICs and microprocessors that you're using. Okay, moving on now to lower operating voltages. So earlier this year we introduced a new family of products, our AXP family. This is the lowest power logic family on the market today. It operates with VCC of 0.7 volts to 2.75 volts. Of course, it's fully compliant to the JEDEC and VIL and VIH standards. And as I said earlier, the static power consumption is 0.3 microamps, and the dynamic power dissipation is 3.1 picofarads. Its typical speed for a standard gate, AND gate, OR gate, is 2.5 nanoseconds pop delay at 1.2 volts. We've also included Schmidt trigger inputs on these devices and also overvoltage tolerance on the inputs. Also included in these devices is the I-off circuitry. As we're starting to see a lot more power management in applications where the power is taken down in one portion of the circuit and kept alive in others. And what the I-off circuitry does is it protects the device from, when this device is powered down, from drawing current even if the input is pulled high or the output is pulled high. These devices also have very low input leakage current, typically in the 0.1 microamps. And they're available in both leaded and leadless packages. Just taking a quick look at the dynamic power dissipation of these devices at 1.2 volts and at the looking at the prop delay, you can see that the AXP device has a typical prop delay. Now this is for a configurable logic device of about 6.5 nanoseconds, and its dynamic power consumption is about 3 picofarads. If you really need high speed, then you have to consider an AUP device, which has, an AUC device, which has a typical prop delay of about 3.5 nanoseconds, but its dynamic power consumption is up there around 17 picofarads. If you look at the power dissipation versus supply voltage, again you see that the AXP is the lowest, and as the supply voltage goes up, the AUC device, its power consumption goes way up from 14 picofarads up to about 20. Okay? So when you look at all the logic families that are out there today that could possibly be used, there are 9 families, and if you look at them at 1.2 volts, there are really only 3 families that you can consider for low voltage applications, and those are the AUC devices from TI, or the AUP device and the AXP devices from, the AUP is offered by TI and NXP and a number of other suppliers, and the AXP is today only available from NXP. But operating at 1.2 volts, if speed is your issue and you really need speed, then of course you have to use the AUC device, which has a typical prop delay of 3.3 nanoseconds. However, if you don't need that extreme speed and you can live with either 5 or 8 nanoseconds prop delay, then you should really consider either the AUP or the AXP, as these 2 devices consume a lot less power than the AUC family. As I mentioned earlier, we released this family earlier this year. Samples are now in production, and in fact, actually the device is fully released to production. We have demo boards and evaluation boards, and I will talk about the evaluation boards later on in this presentation. But you may say, well, you don't have a need today for 1.2 volt or below applications. But doing a survey at a market, we see a lot of products out there. Because NXP's microprocessors operate at 1.2 volts, Renis is at 1.8, But TI has some micros and DSPs that can operate down to 0.9 volts. So if you need to interface these micros or DSPs with some other ASICs, you possibly need an AXP device that will operate at 0.9 volts. Also, Maxim has a 0.9. Freescale has some devices at 0.8 volts. Atmel has a device at 0.7 volts. And it's reported that Cypress and American Semi have devices that will operate down to 0.5 volts. So you can see the trend is to go to lower and lower operating voltage. And the benefit of this is that you need less battery cells. And with less battery cells, you can have smaller batteries, less weight, and less space required. CPUs are typically operating at about 0.85 to 0.75. I came across some Intel CPUs that had the interface at 1.05 volts. Memory, of course, is still up around the 1.5 volts, and some of the ASICs and PLDs are at 1.1 volts. Okay, so moving on now to flexibility and fast turnaround. Also, space savings. And I can combine these three into, address these three needs with our configurable and combination logic. So configurable logic. So what is configurable logic? So configurable logic, first of all, is not programmable. It is configurable. And it's where we put many gates into a single package that can be configured to perform a specific function. So here we have a block diagram of a typical configurable logic device. Okay, and when this device is mounted on a PCB, depending on how you have performed the interconnections on the device, you can configure it to perform one of 9 different specific functions at that particular location on the PCB. For examples, it can be configured to be an AND gate or an OR gate, NAND or NOR buffers or inverters, depending on how you hardwire it on the PCB. It also has some non-standard functions, and the benefit of these non-standard functions I'll point out to you in just a moment. By using a configurable logic device, it offers you flexibility, cost savings, space savings, and also improved system performance. Here we have a configurable device, and you can see that the 9 functions that it can perform. We also offer this device that has level shifting or translation in it, so that you can use it to translate up from a 1.2 volt application to a 3.6 volt application. And I'll talk about that also in just a moment. But first of all, to show you how you configure one of these devices, let's just take the 74AUP1G58. So here in this figure 10, by connecting pins 1, 2, and 6 to ground, using pin 3 as the input and pin 4 as the output, you have a buffer. On the other hand, if you change the hard wiring on the PCB and you just connect pins 1 and 2 to ground and connect pin 5 to VCC, then using pins 3 and 6 as the input and pin 4 as the output, you now have an OR gate. Likewise, by changing the configuration in figure 5, you can make this OR gate into a NAND gate. And so the combinations go on and on, just changing the configuration depending on your need in your application. The benefit of this to the component engineer is that when he qualifies one component, he now has qualified 9 different components at the same time. And also for purchasing, they only have to buy one component and inventory one component, and yet the design engineer has 9 different components at his disposal. You can also configure this device to perform unique functions to save space. So in this figure 6, you can see here that we have an AND gate that also has one of its inputs inverted. how this saves space is that in order to get this function, you would normally have to buy a single gate, an AND gate, an 08 function, and also have to buy an inverter, which is the 04 function, and combine these two devices on a PCB. So you've now got the cost of two components, and you also have the space on the PCB to mount these two components. However, with configurable logic, you can configure the 58 function to perform the exact same function as the combination of the 04 inverter and the 08 AND gate. The other benefit of the configurable logic is that you get an improvement in speed performance. Typically, the prop delay through the buffer is 2.5 nanoseconds, and the prop delay through the AND gate is also about 2.5 nanoseconds, for a combined prop delay of 5 nanoseconds. However, in the 58 function, the combined prop delay is only 2.9 nanoseconds. And the reason for this is that on the 04 function on the left, we don't need to include the higher drive capability, nor do we need to include the ESD protection on the input to the 08 that is connected directly to the inverter. So this is how we improve the dynamic performance of the configurable logic device. Okay, as I said, it can be configured into one of 9 different functions. We have 2 families, LVC and AUP, and we have 4 functions in each. Also, we have an additional function, the 99 function, and this function provides also output enable, so you can turn the device on and off. Since this device is in an 8-lead package, you get an additional 3 functions in the same package. So now you get 12 functions in the package. Another thing that we have done to reduce not only cost but also space. In this example here, you have an ASIC running at 1.8 volts, and you're connecting it to the rest of your circuitry, which is running at 3.6 volts. In order for the ASIC to drive the 3.6 volt circuit, you need a level shifter or a translator. Typically, you would need like an AUP1T34 to level shift up from the 1.8 volts to 3.6 volts. We recognize this need, so what we have now done is taken this translator, the AUP1T34, and built it into our configurable logic device. So by changing the part number you order from an AUP1G57 to an AUP1T57, you get the level shifting or translation already incorporated in the device. Thus, you are saving space because you only have one component on the PCB, and you are also saving cost. All right, so now I show you here the 2 families, the 1G families with adaptive translation level shifting, and then the 1T family. Looking at some of the functions that are available from the 5 different basic functions, you can see that you get the AND gates, the buffers, the inverters, the muxes, NANDs, NORs, and ORs, and the XORs. And these are the traditional standard functions that are used in logic today. You also get the combination logic devices. These are the oddball ones where you can get an AND gate with one of the inputs inverter, or an AND gate or a NOR gate with the input inverted. And these you can use, like I previously said, to reduce the component count on your PCB and also to get better speed performance. So here's the complete spectrum of products. And then earlier this year we introduced our AXP family, the AXP1G57, which this device now operates down to 0.7 volts. We have also a demo board available, and this demo board, as shown here, is configured for the AXP1G57, but you can also put any one of the other 4 configurable logic devices on here. So let me just take one segment from this 4-segment demo board and show you how it works. Here we have the demo board, and depending on how you connect up the jumpers A, B, and C, you can configure it to perform any one of the 9 functions available from a 1G57 device. the demo board itself comes with 4 quadrants, and the 4 quadrants are identical, so you can configure one quadrant to be an AND gate, another one to be an OR gate or a NOR gate, and a MUX, etc., and then string them together just to check out the performance of the device in your application. All right, so the benefits of configurable logic is it reduces the number of components that need to be carried in inventory. It reduces the number of components that are required on a PCB when you're using the out functions. You get better speed performance, and it also saves space and cost. Okay, so now moving down to the final topic, which is combinational logic. So what is combinational logic? Combinational logic is more than one function in a package. And again, we developed this family to help you reduce your cost and also reduce the space required on the PCB to implement your application. Historically, we would put 2 or more functions, 2 or more of the same function in one package. So if you were buying a Pico gate or a MicroPak, you could buy a 2G device that would have a 2G08, which would be 2 AND functions or 2 OR functions or NOR functions. In the larger leaded packages like SO and TSSO, you would get 4 of these functions in the same package. And in the case of buffers and inverters, you would get 6 of them in the same package. However, we started noticing that customers really want to save space, and they don't necessarily need 2 of the same functions in the package. They need 2 different functions in the same package. So that's when we developed the combinational logic, which is more than one function in the same package. The first part we developed, having seen many customers with a need for an AND gate and an OR gate, and these devices were interconnected together, so we decided to combine these 2 functions into one package and call it the 0832. The benefit of this is that the designer only has to select one component, purchasing buys one, saves the cost of the second one, and also one component only needs to be mounted on the PCB. Having developed the 0832, there was also a need to do the reverse, which is the 3208, and so we offer both of these functions. And as we started seeing sales for this device develop, we started recognizing the need for additional combination devices. So here you see a 34 and an 04 function, or 14 and an 04, and 00 and an 02. So we started combining these functions in the same package. If we had 2 of the same 2 independent functions in the same package, we call it a 2G3404, as shown in the top left corner. The middle one here is a 32 and an 08 function in the same package. However, the 2 devices are not independent, they're interconnected, so they really only represent one gate. So as such, we call it a 1G0832. Okay, as opposed to the circuit on the bottom right-hand corner where the 32 and the 08 are independent. In this case, we call it a 2G0832. So combination logic is a method to reduce the package count on your PCB. And you can use existing 2G or 3G gate devices. It also reduces the pin count on the PCB. It reduces the number of packages you need on the PCB. It reduces system costs, assembly costs, etc. So when you look at all of the single input devices that we have and the dual input devices, and when you combine these together, you can come up with 40 single gate combinations, 255 gate combinations, and 355 gate triplet gate combinations. Now you may say that, well, you need one of these oddball and we don't offer in our catalog. And that is correct. However, we can turn these devices around very rapidly because all of these devices come off a master. And it just depends on the last metal there, how we interconnect the metal on the last master to perform one of these 355 functions. Okay, so combination logic is a way to reduce space. We reduce the number of components on a PCB and also to reduce system costs. It also addresses special function needs, and it's available both in LVC and the AUP process. And just to go over the nomenclature again, the LVC and AUP is the family, and then the X is the number of gates that are in the package, and then the Y is the type of function. So if you're using a buffer, it will be an 04. If you're using a AND gate, it would be an 08. So you could make an 0408. So 2G0408 would give you a buffer and an AND gate in the same package. Okay, so that is the bulk of my presentation. I just wanted to go over a few key facts about NXP logic and our participation in the logic industry. We are one of the few logic suppliers that is fully committed and focused on standard logic in the market today. We have grown our market share from 12% to 22% in the last 7 years to become the #1 global logic supplier by volume in the world today. You know, that means that we have 35% of all standard logic devices that are shipped in the world today are NXP logic devices with a PPM 0.15. Okay, we have an extremely large portfolio of advanced products, and for the last 5 years running, we have been the leader in introducing smaller packages. For example, we introduced the GS package, which is a 0.35 pitch 4 years ago. Then we introduced the GN package, which is a 0.3 pitch, 1x1. And just last year, we introduced a diamond package, which was 0.8 by 0.8. However, it has a 0.5 pitch. This is the one that I mentioned earlier that reduces your assembly cost. Okay. We also service the automotive, industrial, and mobile wireless infrastructures. We also do a lot of work in consumer and computing. And just this year, we introduced a new family with the AXP family. Okay, and everything that we design to the AEC Q100 spec. We also implement this in fabrication of our devices and assembly and test of our devices. Okay, and we are further optimizing our manufacturing footprint to ensure ongoing productivity and cost savings for our customers. I will now entertain any questions that you may have. Okay, I see that we have a question, but I don't see the question. I just see the note that we have a question.
Voltage levels.
Here,
Oh. On the right. I think you need to scroll down.
can you read this? I copied it.
Okay, so the question is, how can I translate the AXP voltage levels to standard TTL for the rest of my circuit? So today, the AXP, you can use an open drain function so that you can translate it up to the higher TTL levels that you need. Next question. Yes, so the first part, so the question is, will the AXP logic be available in all standard logic functions like AUP? And the answer to that is yes. The first function that we released was the AXP 1G57. This is the configurable logic device. And the reason we chose that one was so you could configure it to perform one of 9 functions, the ANDs and the ORs, the NANDs and the NORs. We are also releasing and sampling this quarter the 08, the 00, with the 08 is the AND gate, the 00, which is the OR gate. We have buffers and inverters. So it's their intention to release all of the standard functions, the ands, ors, nands, nors, buffers, and inverters, and also to build out the rest of the configurable family, which is not only the 57, but the 58, and the 97, and the 98 functions. What's the next question you have there?
I think you have more questions.
Yeah, but I can't see them.
Question. If you scroll up,
Down.
then that's that. There. Oh. Temperature test.
Yeah, we have a question here on temperature testing. Yeah, we have qualified this to the automotive standard, so we've done extensive qualification testing on the devices. I'm not sure I understand specifically what your question is on different thermal testing. If you're talking about thermal testing, comparing the package on the PCB and the coefficient of expansion of the package material versus the PCB material, yes, we've done extensive testing on that also, and that was illustrated in the reliability testing where we did the band drop testing and vibration testing. That was all covered in all of those testings that we did, and those reports are available. Yeah, so there's a question on the solder paste. Typically for 0.4 mil pad pitch and above, type 3 solder paste is adequate. However, when you go to 0.35 and below, a more costly solder paste, type 4, is required. You see any more questions?
There's one more. Read it.
All right, so the question is, how long would it take to make a specific combination logic device? So worst case is 3 months. If we have wafers that are held at metal, then we can make a device and have your samples in 4 weeks. So anywhere from 4 weeks to 3 months, depending on where the wafers are when the request comes in. Did I say what the question was? How long will it take? Yeah. Okay.
I think that's it.
Okay, if there's no more questions, I thank you for your participation, and I hope this webinar was beneficial to you. Thank you very much.
Thank you all for joining this webinar. You can view the on-demand webinar